Hello, Internet. This is your captain speaking, Lester Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. This is From First Principles, and we are a code red today. As you can see from our background, we had to do this emergency pod as we saw this massive breaking news coming out of NASA of the strongest evidence yet for biosignatures on Mars. So we are going to do a deep dive on alien life, covering 3 stories, starting with that latest breaking news and paper from NASA, which has made waves across the media space. And then we're going to go back for our second story to look at a story from April of this year out of Cambridge, which also claimed to have the strongest evidence yet of life on a distant planet, not Mars. And we'll wrap up with some new discoveries, or at least new analysis from James Webb about the atmosphere on exoplanets that are habitable in the way we think of life. This is going to be a fantastic episode. Let's jump in. My friend.
How's it going?
Episode 8.
We're cooking.
A little emergency pod situation.
Yeah.
We both woke up this morning. I immediately texted you as soon as I saw the news.
Yeah.
Uh,
Press conference and everything.
Everything. Every NASA X Twitter account posted about this.
Yeah.
Obviously, it broke on every science blog and everything.
Yeah.
Because we've sort of had some evidence, but we wanted to make sure, and NASA felt it was good enough to now have the acting administrator of NASA, Sean Duffy, come out and do a victory lap that we might have got him.
Yeah.
We maybe got him.
That's what they say.
So let's start with the breaking news from today. I watched most of the press conference. I'd been following this particular, let's say, sample because at the time it was brought up and people were like, oh, here we go.
Yeah.
But at the same time, everyone was telling me, well, the Hillary Clinton administration said there was strong evidence for biosignatures on Mars 20 years ago. So what's actually different?
Well, this time it seems to be a little bit better than the one that was 20 years ago, but we're actually going to get back to that as part of our story. Okay. So it seems to be a landmark discovery.
Okay.
It is what they're characterizing as a potential biosignature.
Potential.
Okay? And not a full biosignature. A potential biosignature means possibilities that this was a signature of life. But in order to actually really nail it down, what we're going to need is the sample to come back to Earth.
Fair.
And then actually have lab testing with things like electron microscopes and all that other kind of stuff.
So we didn't discover the underground cities and ancient structures on Mars.
Yeah, no channels, no like Martians.
Okay.
It seems to be a tantalizing sign that there might have been microbial life on Mars way back. Back when Mars looked kind of like Earth. Not Earth now, but Earth prehistoric, like right after formation. So the way the solar system formed, there was some giant gas nebula cloud that started spinning. The sun was born. There were outcroppings of small nuclei that became the planets, the rocky planets on the inside. The solar radiation kind of blew out all the lighter gases. So the lighter gases of hydrogen and helium formed the outer planets of Jupiter, Neptune, Saturn.
The gas giants.
Right? And yeah, the gas giants. So right after that, for about 1 billion years, Mars and Earth were both in the habitable zone of the sun. Okay? The reason why Mars looks so different today compared to Earth is because it's just smaller, and so it couldn't hang on to its atmosphere for long enough. And if you can't hang on to your atmosphere for long enough, then the atmospheric pressure decreases like crazy. And if the atmospheric pressure decreases, then you're no longer going to be able to sustain liquid water, right? And liquid water is something that we're pretty sure is essential for life.
Fundamental component.
Fundamentally, we need liquid water as this kind of universal solvent that creates the kind of biochemistry that would be required for something as complex as life.
Asterisks as we know it.
As we know it, yes, yes. Obviously, there could be other forms. I mean, there's people talking about life on the clouds of Venus, on the clouds of Jupiter, and all sorts
But
of
we haven't seen
random
it.
stuff. But we haven't seen it. There could be life in the methane lakes of Titan, but
There
we
could-
haven't seen it.
Well,
Yeah,
there could be $1 billion buried in my backyard, but we haven't seen
but
it.
we haven't seen it. And so, as far as we can tell, we need life. We need water to create life,
Mm-hmm.
right? And anywhere there is liquid water on Earth, there seems to be life.
Mm-hmm.
Even if it's like near boiling,
There's
like near Yellowstone, there's life there, right?
Yep.
So it seems like the one criteria is liquid water.
Right.
You don't even need oxygen. You just need liquid water, and some source of energy. In the case of Mars, that could have just been the sun, or like geological processes on Mars,
Right.
or like the already present compounds on Mars that are somehow, packed with energy that life can then exploit to metabolize. So that's sort of the Mars that NASA's been obsessed with
Right.
for the longest time.
Right.
Okay. This primordial baby Mars that had liquid water.
Right.
We know that now from our several missions there. Actually, the Curiosity rover, which was launched in the 2010s, that had a primary mission of trying to find habitable qualities in Mars. It wasn't trying to look for signatures of life. It was just trying to see, okay, was Mars early in its heyday, was Mars somewhere that could house life? And the Curiosity rover found signs of liquid water, right? And so everyone was really excited. It's like, okay, there's liquid water. The next thing we should do is try to equip a laboratory on Mars that can run around like a rover, and also have all of the tools necessary to sort of do these chemical analyses on the spot and try to look for biosignatures. And that's where the Perseverance rover came in.
This makes sense because the idea is the flight time and flight windows from Earth to Mars are both infrequent and it takes very long.
Yeah.
And so to be able to ascertain before you spend the time and money
Yeah.
to send something back, we want to kind of do a spot check on site.
Yeah. And honestly, like, when the Mars Perseverance rover was launched, I think it was in 2020, during the first Trump administration, there was a 5-year search to figure out where to put it. Okay.
Right.
Because you only got one thing. This thing's the size of an SUV. You got one shot. JPL is worried about, okay, once we have a spot, how do we get it down there?
Jet Propulsion Lab, for those who don't know.
That's the Jet Propulsion Lab out in Pasadena, one of Caltech's little side projects. And so there were 60 different candidate sites
Okay.
that they were trying to figure out.
Oh, they had a
where to
Mars
go.
Love Island.
Yeah. And then there was an international collaboration to try and figure out what is the best place to go.
Right.
Okay. And what they settled on was this place called the Jezero Crater.
Okay.
It's this giant crater. It's about 25 miles across. And we know from the Mars Reconnaissance Orbiter, which is something that just like goes around Mars, has all these like instruments for infrared, visible. From that, we can figure out composition of the soil.
Yep, the
that's
surface.
there, right?
Yep.
The surface chemistry.
Yes.
From that, we had figured out, okay, this is a pretty promising candidate. Also,
And I just want to, because the idea is we're looking for these ingredients that we view as necessary for being valuable to life being able to exist.
Yeah.
We have these tools to detect what's there, and then so we look for the perfect match for those two.
exactly, yeah. And we got about 60 candidates. And then this one was really nice because it's a crater that had that we're pretty sure had like a lake. So it's like one of those crater lakes you can think of as that. And there was a river delta system that was going into it. So there's these beautiful like traces of like literally valleys and like river valleys going into this crater. So, there's a lot of really nice sedimentary rock that's going to be there. And you're going to see if there's life on Mars, that's a really good place to go. Okay. So NASA JPL decided, okay, we're going to go to the Jezero Crater. They landed it there, which is a feat in itself. Right?
Yeah.
This is a SUV packed with like a whole building's worth of lab equipment, right? That like you're trying to drop in. The lab equipment has to be resilient to the heartache of getting off the Earth,
Yes.
going all the way to Mars, then doing a landing on Mars, right? And then everything working.
Everything
perfectly.
works.
And it's still just such a testament to our engineering capabilities
Yep.
that we are able to do this in one shot.
Yep.
And like we're just like really good at it at this point, right? At this point, if like JPL fails and like it crashes, we'd be like, oh, you guys suck. Like, but you know, like it's actually insane
Right.
how many failure modes there are, and none of them ever fail. Like James Webb Space Telescope, there was so many failure modes, and it just like didn't fail,
Right.
Because like the NASA engineers are that good, right? And other countries are like you know, they're crashing on the moon.
Right. They're not even.
This is Mars, dude, with an atmosphere and stuff. Like it's crazy.
MARS. Red rocks.
Yay. Exactly. So we've been obsessed with Mars for a long time. That's been sort of our go-to place to try and find signatures of alien life, right? Even if it's microbial, we want to see that, like, you know, even in terms of life,
Right.
that we're not alone.
I mean, here's the thing. If the part of the point is, if we are able to even confirm, which NASA says we're on the road to, that there is microbial life, not intelligent life,
Yeah.
on the nearest neighbor
Yeah.
that we have in the vastness that is the universe.
Yeah.
That has implications in and of itself, even if it's simply microbial life.
Yeah, yeah. And even if it was something that was there only like 3 billion years ago, right? The fact that it was there, meaning that like the fact that like a planet that was habitable just had life, that's like 2 data points.
Right.
And both have life, right? I mean,
right.
even with Earth's data point, like the fact of the matter is, as soon as Earth was habitable, we have fossils dating back to like that.
Right.
Like before photosynthesis, we have fossils that say, yeah, we had life like basically as soon as the Earth cooled and we had water.
Right. And if we see that now in 2 locations.
Yeah, then it's like, okay, maybe it's actually a pretty ubiquitous phenomenon all across the universe.
In that once you get to the conditions that support life to exist, it does arise not at a low probability, but at a somewhat higher probability than we may currently sort of ascribe to the ability for life to arise.
Yeah. So you know, it'd be a huge deal if we find like...
The point is, this is going to be a big deal.
Yeah, this is going to be a really big deal. And this is only half the story, because obviously, you know, however much we pack onto the Perseverance rover, it's not a lab on Earth, right? We can't put a scanning tunneling microscope up there, okay? That's... even JPL guys will be like, guys, come on.
Right. We can't...
It's literally easier to go and get the stuff back.
Right. Then
right. So it's like, okay, we're making this calculation. Like, why don't we just go and get it, and then just do it here?
Right.
Right.
We'll wait a little longer to get it back.
Yeah. So this is the Jezero Crater.
Yes.
Perseverance was parked right on the outskirts. Did a little bit of traversing around there, and then it went down this valley, down this river valley towards the crater. It went to the spot called the Bright Angel Formation, which is right in the Nare Valley. Okay, it's this like river valley that goes into the crater. Okay, and right over there is something that's really nice, because you've got this sedimentary rock on the western edge of this crater. Okay, and because it's a dry river valley, you're going to have potentially signs of stuff that lived in that water, right? And it's going to leave its markings in the rock, okay? Now, the best thing to do would be to just search for organic compounds.
Okay.
Right? That would be amazing.
Right.
Like just carbon.
Right.
Like we find glucose, we're like, okay.
Right.
We got glucose.
We got it.
Okay. The problem with finding organic compounds on Mars is it's really hard. One is, because it's got no atmosphere and very little magnetic field, there's going to be a lot of radiation from the sun. Right. And that radiation from the sun over the past 3 billion years is just going to completely wreck these organic compounds, right? On top of that, you've got these things called perchlorates, which are chemicals that are highly corrosive. So they're going to react with organic chemistry, and you're not going to go see like amino acids like in abundance. You might see them in trace amounts, but you're not going to find amazing signatures like that.
The idea is the environment, because of the atmospheric dissipation, basically will have destroyed any active evidence of these organic compounds.
Yeah, exactly. So what you want to do is you want to look for inorganic compounds that have signatures of being made by organic chemistry. Okay? And so that's what this story is. Okay? This story is focusing on two classes of compounds. iron phosphates and iron sulfides. So that's iron with phosphate, which is like an SO4, or just an S, or you can have like iron and sulfur, which is the SO4, or you can have iron phosphate. Okay, and phosphorus and sulfur, phosphorus specifically, very much something that is associated with life on Earth. Okay. So finding these things is very, very nice. And that's what they found. They found these iron phosphates and iron sulfides in the rock at this Bright Angel Formation. Okay. And the way that they found these is very conspicuous. Okay. It's very weird. It's not like part of the rock itself. Okay. What they found was, so that you've got this like substrate of rock, which is this mud clay. Okay. It's got a lot of iron. And then you have these like little, they call them poppy seeds and leopard spots. Okay. They're like little tiny, like beads of stuff.
I get if for all the New Yorkers, a poppy seed bagel is heresy when you get your bacon, egg, and cheese if you put on a bagel. But like it would be like looking at a bagel with these little speckles.
Exactly. Yeah. It'll be like looking at, except now it's like this clay
subsurface, right?
Yeah, and then you've got these like speckles, right?
Yep.
And these speckles have these particular minerals that are very exciting to us. Okay. And the other thing that they found was that these speckles have these minerals, right, of iron sulfide and iron phosphate, and the only way that these things could have really happened is through something called a redox reaction. If you know from, this is basic chemistry, you have this thing called the oxidation reduction process. Okay, these reactions are basically ways to transfer electrons from one thing to another, and so you reduce it by taking in electrons, right? Usually it involves oxygen, which is called oxidation, but it doesn't always have to. It's really just a transfer of electrons, and we know that organic chemistry does this really well. Okay, and what they found was like in the underlying clay, they could actually see carbon. Okay, so there was carbon there. And the gradient of carbon was coinciding with how much of this stuff you were seeing. Okay, do you see what I'm saying? So now it's getting exciting. It's like there's a gradient of carbon, which means maybe there was more life on this side than on this side. And the density of this
stuff
of this iron phosphate, which is very on Earth associated with life, is tracking.
It's correlated to the gradient,
of the underlying carbon,
right?
So now it's like, okay, this is pretty nice.
This looks like two data points that are correlating very strongly that we associate with like
organic chemistry, right? And so the idea is you have the starting material, which is this oxidized mudstone, right, which is rich in iron 3, which is an ion of iron. That means that 3 electrons are missing. And then what you do is you have organic carbon, and then that acts like a electron donor to this whole process. And then you have the iron 3 and the SO4, which is an ion that's also found in these inorganic compounds, and then that gets converted into iron 2 and just sulfide, which is just the sulfur atom. So the oxygen goes away. That chemistry is very, very organic-y. Like that chemistry is very life adjacent, if I may say.
If I may say.
Right? So that's the whole point. Everyone's like really excited about this. And one of the impressive things is that we can do all of this on Mars, right? All of this toolkit is on that SUV,
right?
The Mars Perseverance rover,
right?
Which is crazy. It's got this one instrument called PIXL, PIXL, for Planetary Instrument for X-ray Lithochemistry. Basically, it's a way to find the chemical makeup of rocks using an X-ray. They've got a little beam of X-rays that goes in, figures out what comes out. So they've got a detector, and then that tells you
what's in it.
Yeah, what's in it. And then they also have this thing called Sherlock, which is scanning habitable environments with Raman and luminescence for organics and chemicals. I think they started with the acronym, and they're like, okay, how do we make
it fit?
They do this all the time. It's so funny.
Because I don't think chemicals it's Sherlock without a K.
It's Sherlock with a C. But the Sherlock is it does Raman spectroscopy, and it's basically a carbon detector in some sense. So they used the carbon detector to find like carbon on the substrate, and then they used the PIXL instrument to do X-rays on these little tiny poppy seeds and leopard spots to find that, okay, it's iron and sulfur and phosphorus.
And the thing is, I want to just reiterate, there are smart people who thought about this on the front end and had a plan in order to be able to what is the methodology by which you even like ascertain that life was there or not there, etc. Very okay.
Yeah, it's really cool that like they could fit all of this on this giant SUV, pack it into the top of a rocket, have it survive lift off, have it survive landing on Mars,
right?
And then now it's like actually giving us all this crazy data,
right?
And this data is like a year old, so they've been going through it because obviously they know this is like a big deal.
Right. I remember, I believe, Administrator Duffy, as part of his speech in the press conference today, made an emphasis on this point. He's like, we found it last year, and we sent it all over the world because we wanted to be sure. And everyone looked at it, and everyone checked it, and they got back to us, and they were like, you might be right.
Well, so to that point, whenever something like this comes out, this is a big deal, right?
Deal.
The great things about nature is that they make their peer review process completely public.
Yeah, Nature, the publication, not Nature.
Not Nature. Nature, the Springer publication that's been around, that has published all the big papers over the past 100 years.
Yes.
Very recently, they didn't used to do this all the time, but very recently they've made their entire peer review process public. So after something gets published, you can go to the website and you can go to the peer review file and see what the reviewer said. And
that's incredible.
It's pretty cool because science should be open.
Yes.
And just like every grad student knows, there's always one reviewer. Okay. For me it was reviewer 1. For these guys, it's also reviewer number 1.
Of course.
Okay, because they're anonymous.
Yeah.
So if you're anonymous, you can just start saying the most heinous, out of pocket things about the work. And this guy did not hold back. Reviewer 2 and reviewer 3 were pretty nice. They were like, you should include some of these sources. You should maybe word things differently. Reviewer 1 was straight up like, this needs to be rejected. He said that multiple times in his first review. And he's like, the language is bad. First of all, okay, so...
First of all...
He was like, first of all, the title. He goes after the title. He's like, I can't believe you put biosignatures on the title. You look now, the title of the paper does not have biosignatures.
So reviewer 1 won that battle.
Reviewer 1 won that battle because they were like, okay, fine, we'll take out biosignatures out of the title, because he's like, this is only, you can't say that the null hypothesis, which is, that this is of abiotic origin, which it totally could be, right? This chemistry could have formed. We don't know what the chemistry was like 3.5 billion years ago on Mars, right? So it's totally possible that this chemistry could have formed abiotically, right? And so that was his first qualm. His second qualm was about, they have this analysis where they're looking at using the PIXL instrument. They're looking at the composition of these nodules and things like that. And he's like, well, you don't have any clean data, right? Because it's like you have like iron and sulfur, and you're claiming that these are the things that are in it, but there's also all sorts of other stuff, right? And you can look at the rebuttals that the authors put back. Yeah. And so the authors put back the rebuttal, being like, no, the beam of the instrument is as big as the nodules, if not bigger. Right. So I can't focus harder than I already have. Right. This thing is on. It's not like I can remove a lens and put another one in.
Right.
Okay.
Right.
So it's like, this is the best data you're gonna get. Okay. So that one's fine. And it also, he was also like, the language, I can't believe you're calling it poppy seeds and leopard spots. You should be calling it by the scientific terminology, because otherwise people are going to get confused. And so they took that out and they started referring to these things by their scientific thing, which is orthogenic nodules and reaction fronts. Okay,
Which
but they also in their rebuttal they're like, people do this all the time.
Yeah,
like we've heard of Scooby-Doo spots, right? Like people, it's not like it's something that we made up,
Right.
Like it's just a nomenclature,
Right.
Okay, his main qualm was basically like, you guys are like hyping yourselves up way too much. Okay, like I can't believe you're saying it's a biosignature, and then he brings up what happened in 1996. With McKay and the paper in Science.
Yes.
Okay. So this is an incredible story because 1980s, a team finds a meteorite in Antarctica. Okay. In the ice in Antarctica.
That's where the aliens are.
That's what the aliens are. Turns out this guy definitely thought so too. McKay, right? And his colleagues. So this meteorite is discovered in Antarctica.
Yes.
And then because it's on Earth, we can now actually put it under a scanning tunneling microscope and things like that. And we can start looking, and there's these really weird bacteria looking things. Okay. Like it looks like one of those rod bacterias on this meteorite and things like that. And so lo and behold, he's like, this is life, right? It looked like life. Honestly, you look at the photos, I'd be like, oh, that's a bacteria in a scanning tunneling microscope. If you told me that it was from a Mars meteorite, I'd be like, okay, I don't know anymore, right? Because if you tell me it's from a Mars meteorite, the burden of proof has suddenly gone up to here,
right?
Okay, if it's just a rock on Earth, then yeah, there's bacteria on it. So he publishes this thing in Science. It's a huge deal. Okay, Bill Clinton gets in the White House lawn,
right,
and calls a press conference.
Yes.
And he's like, I did not have but he was like, we found life on Mars, and it's great. That's my best Bill Clinton impression. Good. The only thing I can do really is the Monica Lewinsky thing, but I'm trying to. But anyways, so it turns out that probably not right. Just not enough evidence to say that this thing is something from Mars. But it became a huge part of the zeitgeist at the time, because Bill Clinton was also announcing the Human Genome Project. There were all these big wins for American science, and this was going to be one of them. Dan Brown, the author of Angels and Demons, he wrote a book. Yeah, he wrote a book called Deception Point, where it's a great book, and it's the main crux of the story is that somebody finds fossilized aliens in like an iceberg. Right. So it becomes like this huge pop culture thing. And what this reviewer one is saying, he's like, you guys are repeating the mistakes of the past, right? Because the field of astrobiology has already been hurt by this sort of fake hype. And you guys are, quote, the new data set is, quote, much weaker and much less detailed than even what that guy put out in 1996.
Those are fighting words.
Dude, this guy was relentless.
Dude, that's fighting words.
Yeah, so reviewer 2 and reviewer 3, like, reasonable comments. Reviewer 1 is just going ham. Basically, several times he's telling Nature not to publish.
Right.
Okay?
Right.
The authors come back and they say, okay, fine, we refined the language. We're not saying we never said it's biosignature. We said it's potential biosignature, which is something that even NASA agrees and the greater astrobiology community agrees is what this thing should be called, because certainly it is a potential biosignature. This is something, phosphate and sulfur in iron next to organic compounds, certainly something that requires further investigation, and that's what a potential biosignature is. Well, I just thought I was reading the review, and it was just like almost personal.
This is great.
Yeah.
And so we are still in a place, because now that we have the understanding of what are we actually talking about, because a lot of times with these stories of anything related to biosignatures, life off Earth, the news headlines, number one, don't map onto the words in the paper that they cover. Because they're going for clicks. And biosignature is like an amorphous word to 99.9% of everyday people. What does that even mean? But this was actually helpful, because now, in this case, specifically to this research path, we understand what we're trying to say or look for when we say potential biosignature.
Yeah, it's a potential biosignature. It requires further scrutiny.
Yes.
And further lab results.
Yes.
And so actually, what the Perseverance rover did and what it's capable of doing is actually saving samples.
Yep.
So it took a sample out of this guy, saved it.
Yep.
And then, in the future, if we get our funding back, we're going to send stuff there.
To pick up the sample.
Pick it up and then take it back to Earth.
So I think what this means is if we want confirmation that our neighbor, the red planet, remember we're code red today, does in fact not just have potential evidence of biosignatures, but it is in fact biosignatures, we got to go get it.
Yeah.
And in order to go get it, we have to fund the programs that are getting us so close to better understanding our place in the universe. And that what we think of as life is potentially way more abundant than we thought.
Yeah.
But we have to spend the money.
Yeah, we got to spend the money. And the thing is, I think like SpaceX and Blue Origin are in talks, or at least they were before the massive spending cuts.
Yes.
They were in talks to like try to design a mission to do exactly this. Right?
This is a good point. Private aerospace has risen in its power and its efficacy over the last, let's say, 10, 15 years.
Yeah.
Particularly driven by SpaceX with Blue Origin as a close second. Where do they get some, if not a large portion of their capital to even do those things?
Yeah.
Where do they shoot their stuff off from? All government funded.
Yeah.
All government funded.
Yeah.
The
what are they shooting? It's government funded stuff. Yeah. It's not all Starlink satellites.
When we send astronauts up, right?
Yeah.
The government is paying SpaceX to build a capsule to be able to put humans in.
Yeah, I mean, and it's following what the American model for innovation has been for the longest
100%.
time, which is the government spends the money to do all the hard work.
Right.
And then once they figured out all of the little details, now the private sector can come in and be like, oh, okay, I can now do that, and I can do it cheap, and I can do it well, right? That's the same thing that happened with silicon transistors.
Yes.
Right? The government gave a blank check during the Apollo missions to a small company in Silicon Valley that used to be a bunch of apple orchards and orange groves, right? A small company, blank check. I need this size of computer in something like this, and I need it to not overheat. And blank check, do it. I just need it. Okay, we got to beat the Russians. They do it. They're like, well, now I can make computers.
Yes.
Out comes Fairchild Semiconductor, out comes Intel, out comes all of the Silicon Valley tech.
Yes.
Right? So it's a model that's followed, but again, it needs, like, you still need the government to have that money and have that funding to jumpstart these things.
100%. This is not to exclude the idea or the fact that the private industry can and has, particularly in aerospace, pushed the boundaries of innovation.
100%.
But these are not mutually exclusive ideas.
Yeah.
Like, yes, both things can be true.
Yeah.
And both things are true, particularly as we talk about these deeper space missions in particular, where there is no commercial value for a private aerospace company for these more, again, fundamental discovery points.
Yeah, exactly. I mean, maybe you're trying to colonize Mars, but that's like several hundred years away.
Yeah, and not in our lifetime.
Right?
And unless we figure out the longevity issue, which we talked about in last episode, we won't be around for that.
Yeah, I won't be around for that.
So this was the announcement today, September 10th. Took the internet by storm. But this is not the first time, even this year, that we've seen a headline with some version of the language, strongest evidence yet.
Yes.
And so our second story is coming out of the BBC with the headline, scientists find, quote, strongest evidence yet of life on distant planet. This is from April 17th.
That's right.
So almost an identical headline.
Yeah.
Different location, potential biosignatures, strongest evidence yet of life, interchangeable. In this case, for the April story, not on Mars.
No.
But on a very, very distant planet.
Yeah.
And this research was coming from a Cambridge team studying the atmosphere of a planet called K2-18b.
Yeah.
So as a layman, I don't understand what the difference between these two things are when the article just says strongest evidence yet. Which one is stronger? Is this one stronger? Is that one stronger?
Yeah.
Is it the strongest?
In my opinion, I would say the NASA one is stronger.
Okay.
Okay, because you can literally see the stuff.
Yes.
Okay. And at least what we see, we know we see.
Right.
Okay. with this one, it turns out that the paper that came out on April 17th that was purporting to have seen the things that it sees might not have been seeing those things.
So
if
you're
that makes
saying
sense.
don't trust the headlines.
Yes, I'm saying definitely don't trust the headlines. And in this case, also maybe take the scientific paper with a grain of salt. There was a lot of pushback after the scientific paper came out.
Okay.
From the community saying don't say that.
So what's interesting about this April story is, unlike the rover Perseverance being the source of the sort of discovery, quote unquote, it was the James Webb Space Telescope.
That's right.
Another NASA
Yeah,
product.
so there's no tactile evidence. This thing's just looking at
it's
stuff.
just looking at stuff really, really far away.
Yeah. This one's honestly 120 light years away. So in our neighborhood.
Yeah, okay.
Yeah, James Webb is capable of looking, towards
Way,
the beginning of the Big Bang.
The beninging.
Yeah. So this thing is looking at 120 light years away.
Okay.
It's a star called K2-18. It was discovered by the Kepler Space Observatory. And this is K2-18b, so it's the second planet to have been discovered there.
The star's K2-18,
Yeah.
the planet's K2-18b.
B, yeah. And so the planet is a little peculiar for stuff that we talk about in terms of being potentially habitable, because it's not an Earth-like planet. It's bigger than Earth. It's got the radius of 2 Earths. It's got the mass of 8.
Oh.
So it's one of these like mini Neptunes, what we call Hycean worlds. We think that there is a giant ocean on this planet.
Okay. Like in that Interstellar scene where they went on the ocean planet and they had the giant tidal waves.
Yeah. Except this would be a lot deeper ocean.
You wouldn't be able to stand.
Yeah, you wouldn't be able to stand and stuff like that. It kind of reminds me of the planet from Dune that was the home world of the Atreides
Yes.
family.
Yes.
You know,
Yes.
like the beautiful blue planet.
Yes.
It's kind of like that. It's
Okay.
a water world.
Okay.
And it's what we call Hycean worlds in the astrobiology community.
Okay.
Right. And so what they think they found is traces of a gas called dimethyl sulfide. This is the gas that you get with like, cooked cabbage.
Yes.
The smell.
Yes.
That's dimethyl sulfide.
It's
Also
a very
like
particular smell.
Yeah. Also like if you're brewing beer.
Yes.
And then it goes wrong.
Yes.
There's a smell.
Yes.
That's dimethyl sulfide.
Okay.
Okay. And that's mostly just made by like phytoplankton on Earth.
Okay.
Okay. So when we found that on this distant planet,
Phytoplankton must
like-
be there.
yeah, it's like, oh, dope. And honestly, if we found DMS there and there was no doubt of DMS, then it's a pretty strong it's pretty strong evidence. It's not everything, because again, it can happen abiotically,
Biotically.
and that's part of the story that we're going to get to.
Okay.
So first let's try to figure out how we would even like try to find gases on another planet.
Right.
Okay. On Mars you can like literally just like see it. Right. And then with the Mars Perseverance rover, today's news, it can just go and like, oh, it's like it's shooting X-rays and then it sees it.
It's right there.
It's right there. I'm shooting an X-ray. I get the signature.
Not
of sulfur.
120 light years away.
Right. This thing is extremely far. So how do we actually determine what is in its atmosphere?
Right. That's my first question. Is how can we even know that from like from a sensor system?
Yeah, from a sensor, and that's one of the big reasons why everyone was so excited about the James Webb Space Telescope, is because it would have this capability.
Okay.
So here's the idea. The way we find a lot of these planets is through this thing called the transit technique. Okay. What you do is you stare at a star for a very long time. In this case, Kepler did it for a month. You stare at a single patch of the sky and you look at all the stars. And what the star is going to do is it's going to dim every once in a while for a few hours. It's going to dim. And then maybe 2 weeks later, it's going to dim again.
Okay.
And then you're going to wait 2 weeks later, it's going to dim again. And there's going to be a rhythmic dimming. Okay. And what's happening is you're getting an eclipse of the planet
planets
in front of the star.
Because it's basically like if I'm JWST looking this way,
Yeah.
the star is in the center of my field of view.
Yeah.
And the planet is orbiting around. It's eventually going to pass in between me, JWST, looking at the star.
Yeah.
K2-18. and it's gonna be the whoop. And so the dips you're talking about,
That's going to be a transit.
so
That's why we call it a transit method of finding it.
Okay.
And the way that this thing dips is called a transit curve. Right?
Okay.
You're going to see the brightness because these stars are so far away and they're so small for how far away they are that they're basically points of light. Okay. You can't really resolve a circle.
Right.
Okay.
Right,
you just resolve a tiny point of light and all you can tell is its brightness.
Okay.
Okay. And so the brightness goes down and then it goes back up.
Yeah.
And then it's this rhythmic pattern that tells you that there's something orbiting that star.
Right.
That's happening every, 2 weeks to a month or whatever, and has some cadence, and then you can be very sure that that's a planet that I'm looking at.
Yep.
Okay. Now, the nice thing about the transit method is, okay, so you're getting a transit curve for the light, right? The light is dimming, but if you have a spectrograph, which is what the James Webb Space Telescope has, it's got a really nice spectrograph. Okay, especially in the infrared region, which is where a lot of gases do quantum stuff. Okay.
Yes.
So if you've got this spectrograph, what you can do is you can get a transit curve for every color.
Okay.
And the trick is that if there is an atmosphere with stuff in it, then the transit curve for different colors is going to be different.
It's going to have a different,
right? Because if suppose there's a bunch of oxygen on this planet, there's going to be a certain wavelength of light that oxygen really likes, and it's going to absorb a lot of. So what you're going to see is a transit curve for every you're going to see a dip in every single wavelength.
Yes.
But there's going to be one wavelength that you're going to see an even bigger dip because the atmosphere is going to be taking out more of that star.
Yes.
Light.
Yes.
Right?
Yes.
That is fundamentally how we use transit method to find atmospheres on these planets.
The chemical composition of the atmosphere.
Yeah, the chemical composition becomes a kind of barcode across wavelengths.
Because the idea is the light's passing through the atmosphere of the planet on its way to JWST. The atmosphere, if it has certain stuff, is going to absorb that light. So that's what causes on the transit curve the dip to be lower than everything else.
Exactly.
There's a high abundance of that particular
substance. Like for example, suppose we had a spectrometer in the UV range. I don't think the James Webb Space Telescope does, but for sake of argument, suppose there's an alien world out there, right? And it's got a telescope pointed at us, and they're just lucky enough that the Earth is transiting. They got to wait a whole year
for it to come back
around. But let's just say they're super patient.
Yes.
When the Earth goes in front of that star, they're going to see a giant dip in the UV because there's a bunch of ozone, right? Yep. And the ozone is what keeps us from having skin cancer, right? But that's fundamentally because it's shielding us from all of this UV radiation. That alien planet, when it's watching the Earth go in front, it's going to see the rest of the light go down because the Earth is blocking it. But the ozone is just going to be completely obliterated. Right?
Because it's so present in
the because it's so present, right? And so from that, they can then be like, oh, this planet has a lot of ozone. Similarly, that's what we can do with these planets.
So that's how we can understand the atmospheric makeup, which then from that we can draw conclusions from.
Yeah. So that's what these guys did, right? They got this transit from the JWST.
Yes.
And then what they want to do is they want to try to figure out what kind of atmosphere would give me that barcode where this wavelength is a little lower, this wavelength is fine, this wavelength is a little lower, so on and so forth. Right. To do that, now we have to use something like a probabilistic model, this thing called like Bayesian analysis. It's called atmospheric retrieval because we're trying to retrieve the possible atmosphere that created this signature.
Let's say like a barcode.
Yeah. Right? So what you do is you simulate a bunch of different atmospheres with a bunch of different density profiles, temperature profiles, pressure profiles, heights, so on and so forth, where the gas is on what part of the atmosphere. And then you simulate what that would look like on a planet with that particular star, because we know what the star looks like, right?
Right.
We have the spectrum of the star when the planet is not in the
there.
way.
So we know
and
exactly
so
what it
from
is.
that, we then subtract this candidate atmosphere one by one, right?
Yes.
And you create this Bayesian model
Yes.
of all the possible scenarios.
Yes.
And you try to see what model best fits
The barcode we see in real life.
this barcode that we see in real life, right? And so this team out of Cambridge from Niku Madhusudan,
Yes.
he fit a bunch of different atmospheres, and he found that the atmosphere that had DMS and DMDS, which is dimethyl disulfide. So dimethyl sulfide is just CH3, two of these with a sulfur in the middle, and then the dimethyl disulfide is two sulfurs with CH3, CH3.
Yep.
Okay. And what he found was that the best model that fit it was something that had a bunch of DMS and 1,000% more DMDS than we find on Earth. And both of these compounds are very much of biotic origin on Earth. Okay? So he publishes this thing, and immediately the BBC, they love tooting UK's horn. So they're like, oh, strongest evidence yet.
We did it.
Right? We did it.
Even though it was with our stuff.
Yeah, exactly. Yeah, like I'd like to see you try and make a JWST. Right. Anyways, so here's the deal though. You read the paper.
Okay.
And the significance level that these guys are saying is at 3.3 sigma. Okay? 3 standard deviations. Meaning the null hypothesis is there's no DMS and DMDS. This barcode that we saw is a fluke. Okay? And this thing is saying that with about 99.7% certainty, 3 sigma meaning you've got this Gaussian distribution of all the possible things that it can be, and we're 3 standard deviations away from that null hypothesis. Okay? So we're 99.7% certainty. Might seem like a lot.
I mean, if I got a 99.7 with the grade deflation we had at Princeton, I'd be pretty happy.
Yeah. Now, you don't even need grade deflation at that point, right?
Right.
Nowadays, that's an A++++++. Actually, back then that was a B-. But so 99.7% certainty seems like quite a bit. In science, especially in physics and in astrophysics, that is not a lot. The gold standard is 5 sigma.
Okay.
Which is 99.9999%. Okay. 5 sigma is the gold standard for things like the Higgs boson. Okay. I mean, if we had if 3 sigma was the bar for announcing a discovery, we would have discovered the Higgs boson
before CERN.
Yeah. Because Fermilab was doing these experiments already.
Right.
And we were seeing the signature of the Higgs boson. But we didn't do it because we didn't have the 5 sigma level to like actually announce it.
Yes.
So this isn't good practice to announce something at 3 sigma.
So there's a bar.
There's a bar.
So that's sort of like that's mutually agreed upon. That's
by everyone in the community.
You don't publish.
Yeah.
Unless you reach this bar. But then
these guys did it at 3 sigma.
It's funny because I'm looking at this quote in the BBC article from the lead researcher, who said, "This is the strongest evidence yet there is possibly life out there. I can realistically say that we can confirm the signal within 1 to 2 years."
Okay. So he's saying that we can confirm the signal, but then why are you publishing it?
That's kind
of the other thing is like a year before like in 2024, I believe.
Yeah.
There was a thing that came out in the BBC that like it said tantalizing signs of possible life on a faraway world.
I love
okay,
language.
And that was at 1 sigma, 66%.
Yeah, no.
At 66%, I can't believe you're even talking to
media.
The BBC.
Right.
And okay, here's the funny part. That BBC article is written by the same guy who wrote this. So I'm not saying what you think I'm saying, but I'm saying that maybe these two guys are like friends. Okay, right. and like they had dinner, and he said, "Hey, I got like, dude, at 1 sigma, I in science at 1 sigma, you talk to your lab mates about how to improve the sigma,
right?
Okay, you maybe talk to like close collaborators. You don't talk to the media at 1 sigma. That's insane to me. Okay,
66%.
Yeah, 66%, dude. Like that's like a bad coin.
Yeah.
Right.
right.
Like. That's so close to 50. Okay. Anyways, but
I guess.
Understandably, 17th of April, this paper comes out. understandably, there's a lot of backlash from the community.
There's a lot of reviewer number ones.
Yeah. A lot of like, so a week later, this guy, Jake Taylor from Oxford, a week later. So
course.
Oxford and Cambridge, they've always had beef.
Yeah.
This guy comes out and he's like, actually with 5 sigma, I'm telling you, well, actually, like, so he did 6 different other models. With the same data.
This is the model of the potential atmospheres that could match to the barcode. So the idea is Cambridge said, we looked at a bunch of possible barcodes. We found one that's a really close match.
Yeah.
Now, Oxford came back,
and it's like, well, I did like 6 different methods of doing this, and only one of them showed DMS. But 5 of them don't.
So what are you talking about?
So what are you talking about, right?
Right.
5 of these fits don't have any DMS, but they're fitting with this guy pretty nicely.
The accusation is kind of like you cherry picked one.
Yeah.
And you really didn't do
like an exhaustive search.
Right.
And that was a week after this guy published, right? He's a postdoc. He was just like, no.
About a week ago. A week is crazy.
A week, right? And then about 3 weeks later, the Americans start coming in.
We always do. Yeah.
And because we want a little bit more time. So the Wellbanks group at the University of Arizona, they show pretty conclusively that like propine, which is C3H4 abiotic, can also produce the same signature. Okay, so it's like, well, you have you had like certain constraints on your atmospheric retrieval, but now like once we expand the search, there's all these other molecules that sort of fit the bill. University of Chicago does the same thing with all the data, and they're like, I don't see it.
So everybody was like,
everybody's like, bro, what are you doing? And then actually I looked up. The most recent one is the 18th of July, 2025. UCLA, Caltech, and actually Niku Madhusudan, who is the original leader author of the April 17th paper. He's also a co-author in this.
Okay.
And they say that there's probably water on this thing, like a liquid ocean, given the levels of ammonia and nitrogen and methane that we see, like that level suggests that there's liquid ocean. But he also like pulled back on the DMS.
I was gonna say that's a totally different argument.
So he's like there's this, and then the one little sentence of the abstract is like, but the DMS could have been made abiotically actually.
So maybe this BBC article needs a slight correction.
Yeah, they really should like put out a little disclaimer,
because.
Like, or a little asterisk at the bottom being like...
It's funny. The UK always runs to the Americans.
Yeah.
You need the help.
It's so funny. Yeah.
There's sort of been a pivot in the claim.
Yeah.
Which is like, oh, it's probably a liquid planet.
Yeah.
Okay.
But the DMS stuff, let's just...
So the evidence was not the strongest.
No.
So that's a great way to distinguish when you see headlines and it's like... tantalizing, strongest potential evidence of life. What is evidence of life? What type of life? Is it microbial life? Is it intelligent life? Is it a biosignature? Is it a technosignature? There's all these.
Yeah, is it a potential biosignature?
Is it a potential, or is it a direct?
Yeah.
And so with the rover Mars, the reason why Mars is a great laboratory or great research arena is because we can touch and feel and look. It's right there.
It's right there.
It's
yeah,
tangible,
and we can bring it back.
Yeah, if we fund.
Yeah,
the trip back, which we should, because we want to know that there's aliens out there.
Yeah,
but this is a very good contrast, because as many viewers know, and I know like I work at a nonprofit that's sort of addressing this unidentified anomalous phenomena issue. It's funny, I actually tweeted earlier today. X posted whatever people want to say. Yesterday.
Yeah.
Was this UFO hearing in Congress?
Yeah, I heard about that.
In the House Oversight Committee.
And there was like that crazy video.
And there's a crazy video.
Yeah, that looked crazy. I was like, I don't know about this.
It's a crazy video of a Hellfire missile being fired at this object flying over the ocean. It makes contact, but it does nothing to the flight path of the thing that is flying. Mind you, like Hellfire missiles are one of our most sophisticated, advanced. Like it's a problem if it's prosaic or not or anomalous. It's a problem regardless. But the juxtaposition or the sort of fast follow of like that hearing happening, and then I woke up and then NASA's like, oh wait, we might have found life on Mars. It's like, what are you hiding? No, I'm kidding.
And like understandably, like this kind of research and this kind of claim requires an extraordinary amount of evidence
100%.
because this would be one of the biggest discoveries in human history.
Finding out that
Right?
life exists
Elsewhere
is it's in the top 3.
It's in the top 3.
You could argue about whether it's LeBron or Michael Jordan as the GOAT.
Yeah, but like
this is going to be one of those
up there. Yeah, it's either Kobe, LeBron, or Jordan.
Yeah, right.
Like
it's kind of like that situation.
like we can all agree that this is
Right.
going to be a huge deal
Right.
if it comes out, which is why there's so much scrutiny every time somebody says something, right?
makes
Is why I think reviewer 1 on that last paper
yeah.
was so pissed off.
went ham.
Right?
Went absolutely ham. So this is good because we're gonna go to the last story, which kind of creates a nice bookend
Yeah.
for all the fans of the new TV show on Apple TV, The Studio. We need a nice bookend. I love a good bookend.
Mm-hmm.
And so the last story is out of both Scientific American and CBS News. This is also sort of like a brand new breaking story.
Yeah.
Which is, again, another word, hints of atmosphere on Earth-sized exoplanets raises hopes for life. In another James Webb Space Telescope finding.
Yep.
What's interesting about this one is like Halo, they came out guns blazing, dual-wielding research papers.
Yeah.
So there wasn't one.
Yeah.
It was 2 in the Astrophysical Journal letters
Yeah.
related to this hints of atmosphere. So it's sort of great that we just talked through the transit method.
Yes, yeah.
And understanding how would JWST detect the atmosphere from using sensor technology.
Exactly, yeah.
So we have that grounding.
So we have that grounding now. And now we are looking, so this came out September 8th. Very recent.
This was 2 days ago.
Everyone's excited about this because this is a paper on the TRAPPIST.
TRAPPIST-1.
TRAPPIST-1. Have you heard about this?
So TRAPPIST has been, again, because I do the UAP stuff.
Yeah.
A lot of people are
TRAPPIST-1,
that's
everybody loves.
That's where the aliens are.
That's where the aliens are. Everyone's like, that's where the aliens are, right? TRAPPIST-1 is a great little micro lab for solar system research. Okay. The reason for it is it's got a bunch of rocky planets that are all transiting.
Oh, in front of we just talked about
the sun, right? The problem with finding planets is
Yes.
it's incredibly hard to detect, right? Think about think about how we find the planets, right? You were saying that you got to look at this thing.
Yes.
You got to look at the star, and you got to look for the star's brightness to dim.
Yes.
And then you got to wait for it to dim again.
Right.
And then you have 2, and you got to wait for that third because then you know that it's rhythmic.
It's rhythmic.
Right?
Right.
If it's just 2, it could just be 2 random things going in front,
Right.
or whatever, and then know. So you have to wait for that.
Yes.
The other thing is you got to get lucky, right?
Right.
The solar system has to be on edge to our field of view. If you've got a star over here and the solar system is doing this,
it won't pass in front.
it's never going to pass in front, and I'm never going to see it.
Right.
Right. And so the solar system has to have that exact angle
Right.
of being in our line of sight.
Yeah.
Right.
It can't be up here, angle.
So you've got to be incredibly lucky. This thing is not only on edge,
Yeah.
right? It's got a bunch of planets
Yes.
that are all on edge,
Yes.
that are doing this transiting.
Yes.
Also, the transits are very, very short. From 1.5 days to 19 days.
This goes back to what we were talking about earlier. If there was an alien species looking at Earth, our transit time's a year.
A year. They'd have to keep staring at the sun. They'd probably see Mercury.
Right.
And then they'd be like, oh, there's no atmosphere on this thing.
Right, and then give up.
And then give up, right?
And
but
they'd
then they'd see Venus and they'd be like, that's got a hell of an atmosphere,
Right.
But Earth, they'd have to wait 365 days.
Just for once, and then they'd have to wait 2 more years to get the 3.
Yeah, 2 more years to get all 3.
So the fact that the transit's just a couple of days.
Couple of days to 20 days.
It's huge because
huge.
It's because this is a resource allocation issue. If we had a bunch of these tools,
Yeah.
we could just point wherever or leave them forever. It doesn't matter.
Yeah.
But there's limited time, and everyone wants to look at different things for different reasons. And so that's a really good point that the transit time
Is so short.
is so short, which is a
Yeah.
meaningful variable. In
Yeah,
this.
and the other great thing is, so TRAPPIST has a bunch of these planets, right?
Yes.
So imagine you've got a star like this, and you've got a bunch of planets,
Yes.
right? Now, where the habitable zone is,
Yeah.
is kind of nebulous.
Okay.
Right? It's we don't know exactly there's no hard line
Yeah.
of that Goldilocks zone.
Yeah.
But because we've got all of these in a line, even if the habitable zone is here, there's going to be a few planets in there.
Yeah.
Even if the habitable zone is out here, there's going to be a few planets in there. So it's hedging our bets on all of these planets. right? That's why TRAPPIST-1 is very exciting to us.
Okay.
It was found by the TRAPPIST system, which is this transitory planetary project in La Silla, Chile. Really quite small telescopes, to be honest, that are just doing this thing where they just stare at a bunch of stars and then try to do photometry on them to figure out brightness. And it found this thing, I think, in like 2016, and ever since it's been a big part of the exoplanet
research community.
Yeah. So a bunch of planets have been found. As we've looked at it for longer and longer, we know that some of these inner planets do not have an atmosphere. Okay. It makes sense because this solar system is extremely small.
It's like condensed.
It's condensed.
Yeah.
The star itself is an M dwarf. Okay. The classification of stars goes O, B, A, F, G, K, M. We are a G-type star, the sun.
Yep.
M is all the way on the right-hand side of the Hertzsprung-Russell diagram. It's tiny. It's red. It's tiny.
Yeah.
Okay. And so this entire planetary system is condensed inside of the orbit of Mercury.
Oh, wow. So the distance between our sun and Mercury.
Yeah.
All of these planets are
inside there. Okay. Now, that's a good thing because if you've got a really dim star, you want to be close to it in order to like have liquid water and all this other kind of stuff. On the other hand, if you're that close to a star, the star is going to act up. Right. There's going to be solar flares.
Yep.
It's going to be random, like, it's going to like vomit.
Yes.
And then you just get a giant dose of radiation.
Right.
So that's probably why the inner planets don't have an atmosphere anymore because like, okay, like you're too close to the star. Like even though the star is like small, it's still going to be volatile. It's still going to have all these like little outbursts. And so you're kind of screwed there. But the TRAPPIST-1e, which is E is the planet.
Yes.
Now this is, I believe, the fourth planet that's out there. That's something that is kind of Earth-like.
Yes.
Okay. It's about 90% the radius of the Earth, so about 60% the mass.
Yeah.
Which means it's like, if we're on there, we can like at least like hang out.
Yeah.
We'd be jumping a little bit higher.
A little moon-like-ish.
Yeah, a little moon-like-ish, but it's not like something that is completely foreign to us.
Okay.
Right?
Yeah.
The moon is a sixth of Earth's gravity. This is, gonna be like 60%.
It's like a trampoline world.
Yeah. And it's got an equilibrium temperature, they say, of about 250 Kelvin. Okay, so it's a little bit out of where the Earth would be to get Earth's equilibrium temperature, which is around like 280 Kelvin. This is at 250 Kelvin, which is negative 20 degrees Celsius.
Okay.
That's the equilibrium temperature. Now, the thing is, you can have, if you've got an atmosphere, like Venus, you can have a massive greenhouse effect.
Okay.
And then that greenhouse effect can keep
heat in.
And if you have a massive greenhouse effect, the pressure is also higher. So then you can have liquid water, right? So there's a possibility that we could have liquid water on this thing. And we could have types of habitable like qualities on this thing, right? So trying to figure this out is a big problem. Okay. The other cool thing about all of these planets are because they're so close to their sun.
Yes.
Right. They're within the orbit of Mercury.
Yes.
Right. They do this thing called tidal locking, which is something that the Mercury does to the sun and something that the moon does to the Earth.
Yes.
Whenever we look at the moon, we see the same face of the moon.
Right.
And that's because as it rotates, it's also rotating itself.
Yes.
Right. And the rate of rotation
is
matching the rate at which it rotates the Earth.
Yeah.
Right? The Earth doesn't do that, right? The Earth spins once every 24 hours.
Yeah.
Once a day.
Yeah.
And then it takes 365 days to go all the way around. That's why we have 365 days. A day on the moon is also a year on the moon if the Earth is like kind of its center. You know what I mean?
I know
a day on Mercury is also a year on Mercury.
Yeah.
Right?
Yeah.
All of these planets, because they're so close to the sun, they also have this tidal locking, right? Which means they also always face their sun.
The point is there's one side of the rock is always in the sun.
And the other side is always
in the dark. This is why when people say the dark side of the moon, we never see the dark side of the moon. The Chinese can because they landed something and they're over there and we don't know what they're doing. And the national security state is freaking out about that.
Yeah, it's freaking out. Yeah.
But that's as like.
But that's the idea.
That's the idea.
That's the idea. Yeah. So like, that actually causes some problems for like, because the Earth has this dynamic climate a lot of it is because we've got all parts of the Earth getting some sunlight, right? Now imagine like you've got something like this. What kind of world would that be?
Right.
And I was reading about this. It's really cool. They call it the staring eyeball planet.
Okay.
Okay. So what's happening is you've got one part of the planet looking at the sun, right?
Yes.
If this thing is really cold,
Yeah.
then okay, fine. The dark side is just going to be frozen.
Yeah.
But the part that's looking at the sun, there's going to be a central part that is sort of hot and like maybe has liquid water if it has water. Yeah. And then as you go towards the outer parts, you're going to have this middle region where it's like freezing. And so you're going to have this eyeball staring at that sun the whole time, right? Where the central part that is where the sun is always overhead all the time.
Yes.
That's going to be the part that's going to be where
you want
there's going to be this temperate zone, right? Where we would want to live if we ever went there. Which is kind of cool to think about, like a planet that looks like a staring eyeball. Anyways, so they're trying to find the atmosphere on this thing.
Right.
Okay. So you want to do the same thing that you did with the K2-18b.
Yes.
Right. You want to look at this thing. You want to look at the star on its own. Then you want to look at the planet transiting it, and you want to see which wavelengths does the atmosphere, if it has one, absorb. Okay? If it had no atmosphere, every single wavelength would be absorbed at exactly the same amount, and you would just have a flat line, no barcode, right?
Yep.
No barcode, just flat absorption across the spectrum.
Right.
Okay.
To take the bar, just to like really emphasize the barcode analogy, it would be like just having a barcode where all the bars are exactly the same. Like some barcodes like have a little like jigger pattern and this and that, but it would just be like no.
It would just be black.
Yes. Yeah.
There would be no
yeah.
white black markings. Right.
Right.
Yeah. So it would just there would be no barcode.
That's the no atmosphere barcode.
Yeah, that's the no atmosphere barcode. Okay. So they get data from 4 transits because again this thing 20 days. It's so quick. We're like, all right, let's just stare at it.
Right.
They get this thing for 4 different transits, and what you want to do is you want to average them out so that you get like higher signal to noise, right? And it was weird.
Okay.
Because the first 2 times, the transits look way different than the next 2 times. Okay, and that's very strange.
Would it be especially strange, like because it's tidally locked? That would mean we would get, in theory, some more semblance of consistency.
Yeah, because you're getting that same slice, right?
Every
the same
time.
slice every time. And you're thinking that there's not a lot of circulation because this thing is so tidally locked, right? There's not like the thing isn't like revolving underneath where there's like mixing and stuff going on.
Right.
So you would expect that the atmosphere, the atmospheric signature should be static.
Right.
Okay? This is not. So what's happening here? And it turns out that the star itself is pretty volatile.
Okay.
Okay? And so when it's like if the star has, let's say, like a sunspot on it at some point, and then I do a transit versus when the star is just like a normal star. It doesn't have a flare, right? Then you're going to get these different the initial background radiation has signatures that then are getting confounded by the thing in front.
Yep.
Right? And that's why this thing required 2 papers.
I see.
Okay. So the first paper, which is by Espinosa and the colleagues, that one was trying to mitigate something called stellar contamination. Okay. That's the idea of, how do we model the starlight and try to get a clean spectrum out?
It's basically, we want to remove the star's radiation effects. Like, how do we get rid of that noise to get just the planet's atmospheric barcode?
And so that was the Espinosa paper.
Okay.
Then there's the Glidden paper.
Yes.
And that one does a detailed analysis of the spectrum that comes out of the Espinosa paper.
So someone created a model to get rid of the radiation.
So there's a techniques paper.
And
then there's a paper about now that the technique, because the technique, like already like the to do this. Required so much stuff that they're like, this needs to be its own thing. I need a first author on this. All right.
I love
research. Make me a minor author on the other one, but this one I got a career to think about. But it's a really cool way of doing things. They did this again. It's a probabilistic framework.
Right.
They did this thing called Gaussian processes. Okay, which is basically like it's a probabilistic solution where what you're doing is you're like varying all these functions on all the things that the stars could be and like what you're seeing, and then you try to match. And then you try to get like a sort of single combined decontaminated transmission spectrum out, right, of that TRAPPIST 1e.
So the idea is we were originally just getting this like initial barcode that included the contamination.
Yeah, from the star just doing weird stuff.
So now we have like a remixed barcode.
Yeah, to try to get that static atmosphere out.
Just the atmosphere.
Yeah, out of those 4 transits.
So if it's like we wanted a it's like a rap song. It's like no features.
Yeah.
This is the J. Cole album.
Yeah.
We just want J. Cole, no features.
No features, exactly. But you're giving me
we got Young Thug, we got Drake, we got all those other people here, and then I just want J. Cole.
I just want J. Cole. So once they got J. Cole, then the J. Cole went to the Glidden team, and then they're the ones who are like, okay, this is what J. Cole's like.
Yeah, right. Okay, yep. Okay.
Yeah, so the Glidden team then gets this atmosphere out, which is this decontaminated spectrum, and from that they do some analysis. So again, they're going to do the same thing where they have this atmospheric Bayesian retrieval, where they're going to try and fit all these atmospheres. One of the other cool things they did was actually, one of them is this model agnostic. So before even involving the model and like trying to fit like all these different models, they just did like a fundamental physics type of thing, which is like, let's try to figure out how big the molecules are.
Okay.
In atomic units. Atomic units are basically like 1 proton, 1 neutron, okay? So like hydrogen would have a molecular weight of 2 because there's 1 proton, 1 proton, H2, right? Oxygen would have a molecular weight of 32 because it's 16 and 16. 8 protons, 8 neutrons, 8 protons, 8 neutrons to make the O2 molecule. CO2 would be even more. That would be 32 plus 12, which is 44, right? So one can figure out the molecular weight of that atmosphere by modeling the height of the atmosphere, okay? Because if the dominant gas, let's say the dominant gas is of some molecular weight, the higher the molecular weight, the lower the atmosphere is going to be because it's heavier, right? Also, we know the temperature, right? The higher the temperature, the higher the atmosphere is going to be because there's going to be more energy for it to go higher. Also, the higher gravity is, the lower the atmosphere is. But the gravity we can kind of tell based on the density metrics to be like, okay, it's about 60% of Earth. Temperature we can tell based on its distance from the thing, so we can say it's 250 Kelvin. And then the height we can tell by looking at the way that this transit works. Right. By the way that the transit works. And so now we can fit the molecular species. And they found that the lower bound on the molecular weight is about 9 molecular units.
Okay.
Crucially, that means it can't be hydrogen.
Okay.
And that's huge.
Okay.
If it's not a hydrogen-dominated atmosphere, that's a very good thing because that means you've got higher pressures, you've got potentially greenhouse effects going on, right? And you've already just from fundamental physics ruled out that there's probably not hydrogen there. So it's not like one of these Jupiters, right? Jupiter is just like all hydrogen, effectively, right? Like a bunch of helium.
That's
I guess.
So clever.
It's a nice one, right?
No, I
thought that was cool.
No, that's really and again, it's sometimes. I keep coming back to this point every time we talk about these experimental designs is like sometimes it's just about reframing the problem set. Right? It's not necessarily that you need the new shiny thing. Sometimes you could have the data and you just need to kind of come at it at a different entry point and then your follow-ons. Because now, I know you're going to continue. So now that we know that, like, it creates a different context by which you're then analyzing all the other downstream steps in the process.
Yeah. So now you can start simulating atmospheres that don't have hydrogen, right?
Which removes a whole.
Yeah. And so then so what they did was they simulated a bunch of atmospheres. What they're figuring out is there's probably also not a lot of CO2. Okay. Which means that it's not like Mars or Venus. Venus and Mars are basically all CO2. So this one's not like Venus or Mars. They say at this point what they're saying is it's either it's got no atmosphere and we're seeing just noise, or it's got an atmosphere, not hydrogen, not CO2, but perhaps a lot of nitrogen, kind of like the Earth, also kind of like Titan,
right?
And it's got signatures of a lot of methane. We don't see a lot of oxygen, I don't think. Okay. So there's no like photosynthesis going on, which kind of makes sense. I mean, the star is so dim.
Yeah. It's not a big enough power source.
Yeah. I mean, if it was doing photosynthesis, perhaps it's doing a much different kind of photosynthesis because the spectrum of the star is so different from the sun's, right?
Sure.
But nitrogen and methane, which is kind of like Titan, which is very exciting because Titan is also a candidate for potential life. Tantalizing signs, right? And so it also gives credence to like perhaps studying Titan a bit more, right? To see if worlds like Titan are very common in the galaxy, then studying Titan more is going to give us more clues into how this would work. Right.
And Titan's closer. The point is, it's closer. We can do more there, and then we can extrapolate what we learn from that to farther.
Exactly. Yeah. And so that's the whole idea. I mean, they're looking forward to more transits in the future, and actually, what they're going to do that's kind of really cool is they're going to see what a transit on the B planet looks like, because the B planet doesn't have any atmosphere. We know that for sure, right? And so then, if we can figure out what a transit for B looks like and just like get a bunch of that data, then we can model the star transiting a bare rock really well, and then we can have an even better idea on what the transit on the E planet would look like, right? And then we get better data, better signal to noise, better model fitting, higher confidence on whatever's out there.
We need to do Alien Week like Shark Week on the pod.
Every once in a while, whenever there's something cool, like we got to do it.
I mean, literally,
this one was cool, right? The Mars story is very cool.
This week we had not only this hint of atmosphere on Earth-sized exoplanets, which came out 2 days ago on September 8th. We also had the NASA announce a totally separate, totally different context for Mars.
And all four stories are American.
Yeah, look,
right?
Look, you can't avoid us.
You can't avoid us, right? The Mars story is obviously the Perseverance rover and JPL, and then the other three papers, all James Webb, baby.
James Webb, which again, this is why we need to continue to fund science. If you want aliens, we have to fund the fundamental research.
Even if the aliens are looking at us, right? And we give up on science.
They're gonna be like,
man, they almost had
us. They almost had us. And so to do a real quick recap, we started off with the massive breaking news of strongest evidence yet of biosignatures on Mars, announced by NASA, huge press conference, all the things. We then compared that to the April story in the BBC out of Cambridge, which had follow-on papers from Oxford, University of Arizona, University of Chicago, and lastly, the Caltech UCLA combo about strongest evidence yet of life on a distant planet, which we sort of broke down why they've now pivoted to saying maybe it's a water world. And we ended with another follow-up on how we are trying to understand the atmospheres on exoplanets, which is on the path to basically being able to identify what targets really make sense for us to look for life. Very informative, very clarifying. I wish we got this kind of clarity in the articles that most people read. And so if you are watching this and this was super helpful, please share it with your friends who might be interested in this subject, because again, like understanding like what are we actually saying when we say what is the evidence, what is a biosignature,
and it's like not that hard to understand.
No, it's not,
right? It's like if you like go through it and like just go through step by step. It's like, okay, this is the data that we collected, this is why we think that data says what we think it says, right, and these are the limitations, these are what we can do next. It's like it's not that crazy difficult to understand the logical steps required to conclude to get to the conclusion.
We're looking for 5 sigma significance plus. And I'll just do a quick housekeeping. The response has been unbelievable to the show. We really appreciate everyone. If you've watched all the way to this part of the show, that means you're a true fan. We really appreciate you. We are literally one of the fastest growing science podcasts on the planet.
It's unbelievable to us.
It's unbelievable. It's gone global. Just continue to add your comments, add your questions, add your clarifications. You can always find all of our episodes anywhere you like to listen to your podcasts, on YouTube, Spotify, Apple. We post clips all over our socials on Instagram and TikTok and Facebook and X. So you can find us where you want to. I, as always, am your host, Lester Nare, joined, as always, by one of the smartest people I know, our co-host and resident PhD, Krishna Choudhary. This is From First Principles, an amazing emergency pod. We'll be back next week for regularly scheduled programming. Appreciate you guys. Peace.